Hello everybody and welcome back. I hope you're all as excited as I am. We're looking at question number 4 on the 2004 Hypatia contest. Okay, this is the last question. It's going to wrap up the Hypatia for us. What have we got here? So, 3 parts for this question, and it looks like we've got different balls placed in a bag. So let's read part A and see where our mind takes us. 1 green, 1 yellow, and 2 red balls are placed in a bag. 2 balls of different colors are selected at random. These 2 balls are then removed and replaced with 1 ball of the 3rd color. Enough extra balls of each color are kept to the side for this purpose. This process continues until there is only 1 ball left in the bag, or all the balls are the same color. What is the color of the ball or balls that remain at the end? Okay. So, for example, we could take out a green and a yellow, and we'd replace them with 1 red ball. And then it would have to be 3 red balls, and so the answer would be red. But that doesn't mean that that's what happens. What if we took out a red and a yellow ball? Well, then we'd take them out, we'd put in a green ball. That sort of thing. Okay? So, naively, the way the question is worded, because they're saying what is the color, just do it in your head once, just pick out some different balls. We mentally did it once, and the answer is going to be red. But this is the Hypatia. This is not the Fermat where you just need your final answer. We got to show that it's going to be red. Not only that, we should probably show it's going to be red no matter what we do. Now, unfortunately, we're given just 1 green, 1 yellow, and 2 red. There's not a whole lot of combinations we can do here. So I'm just going to write them all out until I see a better way to do this. Okay? So, it should be red, but let's show that no matter how we do this, it's going to be red. So, because I don't want to write green, yellow, and red a whole lot, let G be green, Y equal yellow, and R equal red. Okay? So we start with 1 green, 1 yellow, and 2, not blue, red. Red. Okay. So if we took out one green and 1 yellow, we'd put back 1 red for a total of 3 red, so red is the last color. But we could have taken out 1 green, 1 red, and we would have put back 1 yellow. So then we would have had a total of, we'd have 2 yellows, and 1 red. Well, then we have to take out 1 yellow, 1 red, because the process repeats, and that'll put back 1 green, so we'll have a total of 1 yellow. One of them was left over. We only took 1 of the 2 yellows out, and 1 green, and they get taken out 1 red, and it'll be red. And the other option is we could have taken out a yellow and a red to start. And this should also end with 1 red ball. So we could have taken 1 yellow, 1 red, and then we would have put back 1 green. So now in total we still have 1 of our 2 reds. Now we have 2 greens. And it's going to work the exact same way it did with the yellows in place of greens for the last one. So we must take out 1 green, 1 red, and that puts back 1 yellow. So in total we have 1 yellow and 1 green. Must take 1 yellow, 1 green, and we put back 1 red, and that will end with a red as well. So if you wanted to, you might explain why you have to take out 1 green, 1 red here, because there's no way you can take out one of them being a yellow. But really, I think just detailing exactly how it's going to go is enough here. Maybe use a bit more complete sentences than I do, but really, the points are there. Okay, and I do mean key points, not like check mark points, not the marks. I think the marks are there too, but my point is the key points are there, whether or not you use complete sentences or just enough information and symbols to get your point across, as long as it's written clearly. Okay. Part A is usually, especially if it's a three-parter or a four-parter. Part A is always the introduction. Do a simple calculation so we know you understand at least the setup of what's going on. B and C, those are the ones that are going to say you got to develop a theory. You need to know what's happening in general. This is just the mucking about. Do you understand how the balls are being removed? So don't waste too much time on it. So with I have no idea why I wrote with. I can't think of what sentence I'd be writing. But so with each of the possible. No, I don't. I shouldn't be. Don't build off the with. No idea what past me was thinking. So no matter how we remove the balls, we eventually have only reds. Okay, it might be 3 reds, it just might be 1 red, but eventually it's only going to be red. Okay, so that's A part. Nothing to stress about. Now B part. Looks like we have more balls. So 3 green, 4 yellow, and 5 red are placed in a bag. If the procedure is repeated, what's the color of the ball or balls that remain at the end? So they seem pretty confident with their use of the definite article that the answer will be color no matter how we do this. The green ball at the end, or like 4 green balls or something like that. Or maybe it's yellow, I don't know. Maybe it's always red, although these rules seem independent of red. They seem quite symmetric. Just because C will likely build off this and ask us to make a bigger theory or something, let's just read what C is. So same number of balls, 3 green, 4 yellow, and 5 red placed in the bag. This time 2 balls of different colors are selected at random, removed, and replaced with 2 balls of the third color. Show that it is impossible for all the remaining balls to be the same color, no matter how many times this process is repeated. Alright, so it's not really building off the process we saw in parts A and B, but it's tweaking it ever so slightly. So we can carry out B and we'll worry about C later. Maybe we'll learn some stuff on our way to C through B, but now we should be fine. So 3 green, 4 yellow, 5 red. I don't want to write out all the possibilities here. So what I'm going to do, because I've seen some questions like this in the past. I mean, I've even done a small little 10-minute workshop with some people, picking marbles out of a bag as part of a special teaching project. Not important, but the point is, I've seen questions like this. I've also seen it phrased like you've got chameleons of 3 different colors. You have if a green chameleon and a yellow chameleon meet, they get startled and both turn into red chameleons. So I've seen some of these questions before. Now maybe this is the first time you've seen a question like this, and that's okay. You're going to learn as we go here. But if you have seen something like this, you know what? We're sort of going to need to not take a look specifically at, we have 7 greens and 2 reds left, and that'll, we can only pick this stuff and this. What you need to do is analyze the rules. How does this set of balls possibly change into, this set or this set or this set? What do the rules tell us? And what we often look for is not how are the rules changing, but what things are staying the same. Okay? So what you can often have is something like, the number of yellow balls will always be even, or, there's always going to be 1 more green ball than there are red balls, that sort of thing. Something that doesn't change no matter how we picked out the balls at random. Something that doesn't change. And this is called an invariant. Okay, I'm not going to do more of this, but maybe I'll record the marble thing at some point in the future. But that said, what I want to do is analyze the rules rather than take a look at the 3 green, 4 yellow, and 5 red. And this is also going to be what I think we need to do for C part. We're going to need to analyze the rules and sort of show that there is no invariant. And there is no way to get everything being the same color. Or rather show that there's an invariant that makes it so you can never have them all the same color. But what are we to do here? So let's take a look at the rules. So our rules, we've got 3 rules basically. So we've got the things we take and the things we put. So we take out 1 green, 1 yellow, and 0 red. And so we subtract these guys off, and we add in 1 red. And we subtract 1 green and 1 red, and we put back 1 yellow. And then what's the other thing we could do? We could not take out any greens. We could take out a yellow. We could take out a red. And we could put back a green. So plus 1 green. Okay, so basically what we're doing is we remove 2 of one color and add a third color. So, what to do? So basically our rules are more, we just sort of all at once add this number. Let's be a little more clear. So to go from having G greens, Y yellows, and R reds to some new state. No, I don't want to write it that way either. I'm trying to think of the clearest way to write this, and that's a good idea, is to think how you want to express your ideas clearly. Obviously, you know what you're thinking, but part of creating a proof, part of doing a written question is being able to convey that you know what you're talking about, and making it so someone else can read it. So I'm going to say something like G, Y, and R represent having G greens, Y yellows, and R reds in the bag. Okay. So then our rules basically amount to, we can go from G, Y, and R to, well, we could do G minus 1, Y minus 1, R plus 1. Or we could do G minus 1, Y plus 1, R minus 1. Or we could do G plus 1, Y minus 1, R minus 1. So I asked myself, what has changed? I think no. I think it might be some sort of evenness, oddness thing. That's what I'm thinking. Okay, so let's see here. Because adding 1 and subtracting 1, I mean, this doesn't change. So overall, this is what I'm going to do. Let's look at evenness and oddness. Okay? So, yes, the actual numbers of red marbles might be decreasing and the number of yellow marbles, but perhaps the number of odds and evens might not be changing. So I think that might be key here. I think so. I'm not entirely sure, but I think that's what it is. So if I start with, say, something that's even, odd, and odd. So I have an even number of greens, an odd number of yellows and an odd number of reds, I will get out an even minus 1 is an odd minus 1 is even, and an odd plus 1 is even. Or I could get an odd, an even, and an even again. Or, okay, an even plus 1 is odd, and then even, even, even. Okay. And this is going to be true of just about everything. So if I had an odd number of greens and an even number of yellows and an odd number of reds, I'm still just going to get even, odd, even. Even, odd, even, no matter how I do these rules. No matter which rule I do, all the even numbers are either decreased or increased by 1 to become odd, and all the odd numbers are increased or decreased by 1 to become even. So what I've learned here is after a step in the process, an odd number of one color will now be even, and an even number of one color will be odd. Okay. So we start part B with 3 green, 4 yellow, and 5 red. So that's an odd number of green, an even number of yellow, and an odd number of red. To have only one color left, will be to have 0 of 2 other colors. And we know 0 is even. So we'll have to have even, odd, even, right? Because what can happen? We can go, we start off with an even number of greens, or sorry, an odd number of greens, even number of yellows, odd number of reds, and that will automatically go and flop around like this. No matter what rule we use, the take out a green and a yellow rule, take out a green and a red rule, or take out the yellow and the red rule. It doesn't matter which one. And then on the next step, we'll be looking at even, odd, even. No matter what the actual numbers are, it'll still be even, odd, even as the pattern. And it's just going to go back to odd, odd, even. So we must end up with even for 0. We'll write 0 out because he looks like my odd. So we'll end up with even, odd, even. So only yellow will be left. Okay. Does this make sense in the context of A part? Same rules, and we start with odd, odd, even. So after one step, we'll be even, even, odd. And then after another step, we'll be back to odd numbers of green, odd numbers of yellow, and even numbers of red. And this will keep going. Now, eventually, we'll have to stop with 2 of them being 0 balls of that color. The only way that'll happen is if we go even, even, odd, and so it'll have to be red balls left. And not only did we get that red balls had to be left, but each time we either had 3 red balls or 1 red ball, we did have an odd number of red balls. So our theory really does work, looking at it from the oddness, evenness. Okay. Now I'm going to add just a little extra line to point out that we're just not going to go in some weird cycle. Okay, now in since, we decrease the total number of balls by 1 each time, we will eventually get down 1 ball, and so that'll have to be 0, 1, 0. So we're not stuck in any sort of loop. And this completes our proof. Okay? We will always get yellow. Because it could have completely transpired that the way the rules were set up, you know, the number of balls doesn't actually change overall, so you're never going to decrease. And so, yeah, you're always going to go even, odd, odd, and then odd, even, odd. Those will always be how you look. But maybe you'll never get down to only one of one color. You'll never get those zeros. But we're guaranteed to eventually have this sort of state at the end, when all else fails, of having only 1 ball, and the other 2 have to have 0. Okay, you can't have negative number of balls. All right? So we did need to include that, because maybe there's some way, maybe it only goes 2 green, 3 yellow, 2 red, and then the next step is 3 green, 2 yellow, and 1 red, and so, you know, bad example. But maybe it only goes like 2, 2, 2, and then it goes 1, 3, so not 2, 2, 2, 2, 3, 2, then maybe it goes 3, 2, 2, or 2, 2, 3, and it just keeps cycling around and nothing actually happens. That's something that could happen, but it doesn't happen in this case, so we have to double check that. I don't think I made that clear. Okay. So we got 1 bit left to go, C part. So same number, 3 green, 4 yellow, 5 red, but now the rules have changed. 2 balls of different colors are selected and removed and replaced with 2 balls of the third color. This, I think, will make it impossible for all the remaining balls to be the same color. So let's look at the rules again. So we'll look at it more generally. Green, yellow was in the middle, wasn't it? So we sort of have new rules. Green, yellow, and red. And now what could happen? Well, we could remove a green, a yellow, and add 2 reds. We could move a green, we could add 2 yellows, and remove a red. Or we could add 2 greens by removing a yellow and a red. So those are our new rules. Now, the last rules, we noticed that, oh, we're minusing 1, we're adding 1. Really, we're just changing the parity, the oddness, evenness. But this time, this is not what's happening. Okay? -1 and +2, if you started with odd, even, odd, and you took out the green and red, the green and reds would now be an odd number, or an even number of them. But we'd add on 2 yellows, and yellow is already even, so you get even, even, even. So it's not the oddness or evenness that is really the thing that's impervious to change. What we have to do is look at our rules. And the way it worked last time is -1 and +1. These are basically the same things when it comes to just looking at oddness or evenness. But -1 and 2 are not the same thing if you're looking at things in terms of remainder when you divide by 2. So B -1 +1, so that was our x -1, x +1. You have same remainder when divided by 2. So we looked at odd and even. Okay? But now in C part, our rules are, well, something's going to go down by 1 and something goes up by 2. How can we view this, each of these different rules as really sort of the same process? Okay? And this is true not if we give same remainder when we divide by 2, but when we divide by 3. So what we're going to do is we're going to look at this problem modulo 3, everything just as, you know, your remainders when you divide by 3. That's how we're going to view this problem. Okay? So we're looking at the problem. If we want to be fancy, we say modulo 3. But really what we mean by that is just, you know, we don't care about multiples of 3. It's all about the 0, 1, or 2. What's your remainder when you divide by 3? So if we do that, we only have one rule. And that would be, well, they sort of go to the same thing. Okay? They don't really change a whole lot. Not that these numbers, I mean, the remainders they all go down by the same amount, or they all increase by 2. But the point is, if we look at the total here, g plus y plus r, that's going to be the same. Not the same, but has the same remainder as g minus 1 plus y minus 1 plus r minus 1 when we divide by 3. Okay, because it's just g plus y plus r minus 3. So it's going to be the same when we divide by 3, because that minus 3 doesn't really impact anything. Okay, so let's look at the total, the divisible, the remainder of the total when we divide by 3 doesn't change. Okay. So the total we start with is 3, 4, 5, which has, or this is what we start with. We start with has a total of 3 plus 4 plus 5 is 12, which is 0 when we're working modulo 3. The 0 is the remainder. Okay, so really these guys add up to 0. So the remainders, mod 3, are, well, it's 3, 4, and 5, but really that's 3 has a remainder of 0, 4 has a remainder of 1, and 5 has a remainder of 2. And what does our rule do? So our rule, it would take something in like this, and then what we do is we just sort of decrease everything by 1. So 0 goes to a remainder of 2, because if you take something like 6 and you subtract 1, you have 5, which has a remainder of 2. 1, well, we lose one of those, you get a remainder of 1, or of 0, and 2 goes down to 1. And then this goes down to 1, 2, 0. And then we're back to the start again. Okay? So, because, I mean, look what would actually happen with the real rule. So maybe we take away a green and a red, and we add in two, or not a green and a red, a green and a yellow, and we add in 2 reds. So that was 0, 1, 2 for the remainders. Now it's 2, 0, 1 for the remainders. Now maybe we take out a green and a red, and we add in 2 yellows. Suddenly you're looking at 1, 2, and 0, just as predicted. And then we'll be back to our start again. So maybe we'll take out a green and a red again. We'd get 0, 5, and then this guy will bump up to 7. So a remainder of 0, remainder of 1, and remainder of 2. So this really does work. It does sort of go in a cycle. And because these remainders cycle, so the remainders mod 3 cycle, but there is always one of remainder 0, one of 1, and one of 2. Now, to have only one ball, or have only one color left, means the other two colors have 0 balls. But that would mean we have 2 colors, at least, of remainder 0. This can't happen. Right? It can't happen because, if those two were 0, then what's the third one? Is it the 1 or is it the 2? Because we always have one remainder of 0, one remainder of 1, and one remainder of 2. And now you're saying, oh, we somehow managed to have just one color remaining. Then the other two colors have to have 0, which is a remainder of 0. So we'd have 2 remainders of 0. And then either one remainder of 1, one remainder of 2, or even a third remainder of 0. But that can't happen. Our rules go 0, 1, 2, 2, 0, 1, 1, 2, 0, and then we're back to 0, 1, 2. It just keeps cycling. So, and you can test this at home. No matter how many of this rule you apply, you'll always have, one of them is going to be, only one of them is going to be a multiple of 3. We start off with green being the multiple of 3, and then we'll shift to yellow being the multiple of 3, then we'll shift to red being the multiple of 3, then green will be the multiple of 3 again. Now, eventually some of these might be 0, but there'll never be another 0, because that would be another multiple of 3, and there's only one multiple of 3 allowed. And that's what we sort of stated here. I admit it could probably be cleaned up. Usually my 4s and my 10s on the Euclids could be cleaned up a little bit, but the essence is there. It remains for you to be someone who says, I want complete sentences, or I think more jot notes would be fine. And as usual, I've used the notepad both as my solution and my scratch pad, which is not good. If you have the time, go back and clean up your workings and just leave your answer. You don't have to show your work. Sorry, you have to show your work. You don't have to show where you got your ideas from. So think about if you were doing a game theory question. You don't have to show like the fiddly 2 pages of work that you got and now I understand Alphonse's winning strategy. No, you take all that work you did, but that's rough work. You state Alphonse's strategy and then you state the proof why it works. Okay? You do a whole bunch of work on this question and you realize, we use remainder 3. Erase all that stuff when you write up your good copy. You usually do that stuff rough work and then write the good stuff in the booklet. And then in the booklet, it's just, we're inspired that we have remainder 3. You don't have to motivate that. You don't have to say, I looked at this for 20 minutes and I'm pretty sure remainder 3. Just start off, let's look at the problem with remainders when we divide by 3. Right? You just start off that way. So I took a little while to get there, because again, this is both my rough work and my solutions, but hopefully you guys will clean things up a bit more. Okay, but I think all that said, we're done here. We've got, that was question 4 on the Hypatia, and the FGHs, they only have 4 questions, so I liked that one. I think question 3 was a little easy, question 2 was quite easy, and question 1, question 1's always easy. But, I expect a little more from my grade 11 Hypatias, and they did get, this is only the second year they did the contest. They get harder later. So if you're looking for another Hypatia, the next one I will be doing is the 2005. I think the next contest I'm going to post, if I remember my schedule properly, is going to be a Euclid, so the 2004 Euclid. So that'll be another written contest, and we'll see how that goes. But thank you guys for watching, and you don't have to go see the 2004 Euclid. You can bounce around, do the 2000 grade 7 Gauss or something like that. So you do what you want, and I'll see you guys in the next video no matter what it is.